Welcome you all to the course on discrete time signal processing. Myself Mr. K. Arun Kumar. This lecture is about design of bandstop FIR filter using windowing method. Okay, so directly I hope we all know. So what do you mean by a bandstop filter? So it is nothing but the range of frequencies will be blocked. Okay, so the frequencies which is lesser than the cutoff frequency 1 will be allowed, and which is greater than the cutoff frequency 2 also will be allowed. Okay, frequency will not be allowed between the frequencies omega c1 and omega c2. Okay, now directly we will move on to the problem. So here I given design and realize a bandstop filter that is having a ideal response so and so, that is hd of e power j omega is equal to 1 for mod of omega less than or is equal to pi by 6, 0 for the range pi by 6 less than or is equal to omega less than or is equal to pi by 3, and 1 for the range pi by 3 less than or is equal to omega less than or is equal to pi, using Hamming window with order n is equal to 7. Okay, this is a given ideal response for us. Now first we should draw the diagram. Okay, so we will draw the frequency response, that is omega versus hd of e power j omega. Let us take x axis omega and y axis hd of e power j omega. They mentioned that mod of omega, which means that the frequency is from minus pi by 6 to plus pi by 6. Okay, for that particular range the frequency value is the magnet value is 1. Similarly, for the second category, that is from pi by 6 to pi by 3, the value is 0. From pi by 3 to pi, the value is 1. Okay, so it is a symmetry filter, then the same has to be replicated in the left side also. Okay, and this is 0 and this is 1. Okay, now they are asking us to using they are asking us to design this filter using Hamming window for the order n is equal to 7. I think we know the procedure for to design a FIR filter using windowing method. The first step is we have to find the value of hd of n. The second step we have to find the value of windowing sequence w of n. In the third step we have to get the impulse response h of n. Fourth step transfer function. Fifth step realizable transfer function. Sixth step structure realization or the frequency response, that is based on the problem. Okay, so as per the procedure, the step 1 is we have to find the value of h of n, that is hd of n, desired impulse response, which is nothing but the formula says that 1 by 2 pi integral over minus pi to plus pi hd of e power j omega into e power j omega n d omega. Okay, for the range from minus pi to plus pi, for all the frequencies the magnitudes are not same. Okay, we have two different values, that is one is 0, the other one is 1. Okay, now the value 1 exists for the range from minus pi to minus pi by 3 and minus pi by 6 to plus pi by 6, as well as from plus pi by 3 to plus pi. Only for this 3 particular range the value is 1. For rest of the values or for rest of the ranges the value is 0. Now I am splitting the integral from minus pi to minus pi by 3, the magnitude is 1 into e power j omega n d omega, and for the second one the magnitude is 1 for the range minus pi by 6 to plus pi by 6 into e power j omega n d omega. For third one is the range is pi by 3 to pi, the magnitude is once again 1 into e power j omega n d omega. Now we have to integrate this. So the integral of e power j omega n is nothing but e power j omega n divided by j n. This is for all. Okay, now we can substitute the upper limit as well as the lower limits. After substituting upper limit and lower limits, we can group together. Okay, so this is looks like e power j theta minus e power minus j theta. Okay, e power j theta minus e power minus j theta. As per Euler's theorem, this is nothing but 2j sin theta. Okay, that is 2j sin n pi by 6, and that's what I wrote here, 2j sin n pi by 6. Okay, and coming to this 2, that is e power j n pi by j n minus e power minus j n pi by j n. Okay, this also similar like e power j theta minus e to the power of minus j theta. Okay, Once again, as per Euler's theorem, I can say that it is 2j sin theta. So, 2j sin n pi. And the last one, so this is e power minus j n pi by 3. Okay. This is e power minus e power j n pi by 3. Okay. So, I am not getting the standard format. So, I am taking minus common. Okay. If I take minus common, this will become e power j n pi by 3 minus e to the power of minus j n pi by 3. Okay. E to the power of minus j n pi by 3. So, now based on Euler's theorem, I can say that it is 2 minus 2j sin n pi by 3. Okay. And we all knows that sin n pi is always 0. So, this term will become 0. Okay. So, in the first two terms 2j is common, I can take 2j common out and j will get cancels, 2 also will get cancels. Finally, I am getting hd of n is equal to 1 divided by n pi sin n pi by 6 minus sin n pi by 3. The range for small n is minus of capital N minus 1 by 2 to plus of capital N minus 1 by 2. For our problem, the value of n is nothing but 7. So, 7 minus 1 by 2 is 3. So, the range for small n is minus 3 to plus 3. Okay. This is one of the way. Okay. The other ways I will give very shortcut method. For any band pass filter, just look at this. For any band pass filter, the desired impulse response is given as 1 by n pi sin of n omega c1 minus sin of n omega c2, where omega c1 and omega c2 represents cutoff frequency 1 in terms of radians per second, cutoff frequency 2 in terms of radians per second. Now, go back to our design, okay, and try to calculate or try to find the value of omega c1 and omega c2. Okay. So, this is omega c1 and this is omega c2. Okay. Omega c1 is pi by 6, omega c2 is pi by 3. Now, take this value and come back to your equation or standard format. Now, substitute omega c1 is equal to pi by 6, omega c2 is equal to pi by 3. So, that is nothing but hd of n is equal to 1 by n pi sin n pi by 6 minus sin n pi by 3. So, the range for n once again the same. So, minus 3 to plus 3. Okay. We can follow any the previous one or this shortcut method also. Okay. This is only for band stop filter. Okay. We will have different hd of n for band pass as well as low pass and high pass. Okay. After finding hd of n, our next objectives we have to go for windowing sequence. Okay. Okay. Before going for windowing sequence, first we should find out the values. Okay. What is the range for n? So, this is minus 3 to plus 3. So, we have to substitute n is equal to minus 3, n is equal to minus 2, n is equal to minus 1, n is equal to 0, 1, 2 and 3. All this value we have to substitute and we have to find the values. Okay. So, hd of minus 3 is equal to, okay. So, just substitute the value n is equal to minus 3, okay, and keep your calc in the radian mode, do not keep in the degree mode. Okay. Keep your calc in the radian mode and find these values. Okay. That is giving hd of minus 3 is equal to minus 0.106. Okay. Then if I substitute n is equal to minus 2, I am getting 0. Then if I substitute n is equal to, I am getting 0.116. Okay. But while coming to n is equal to 0, okay, so you can look at this, this is 1 by n pi. If I take n is equal to 0, which will become 1 by 0, it is not defined, that is infinity. Okay. In that case, either you can go for L hospital rule or initially once again you can derive this hd of n by substituting n is equal to 0. Okay. I will take n is equal to 0 in this formula, 1 by 2 pi e power j into omega into n, n value is 0, e power 0 is 1. Okay. Now, it is only integral of d omega for all the 3 cases. Now, once again you can substitute the upper limit and lower limit and you can cancel the values which are in opposite sign, and finally, I am getting hd of 0 is equal to 0.833. Okay. Now, once again we should substitute the value of n is equal to 1. Okay. So far I have completed minus 3, minus 2, minus 1 and 0. Now, if you go for 1, it is once again is equivalent to hd of minus 1. Okay. If I try to find a value at n is equal to, which will be equivalent for n is equal to minus 2. Okay. Then if I trying to find HD of 3, which will be equivalent to HD of minus 3. Okay. And that is what I told initially while starting of this problem. So, it always produces symmetry response. Okay. So, HD of minus 3 is equal to HD of 3, HD of minus 2 is equal to HD of 2, HD of minus 1 is equal to HD of 1, and HD of 0 is the center of symmetry. So far we have completed step number 1. Second step, windowing sequence. Okay. Here they are asking us to follow Hamming window. Okay. The sequence for Hamming window is W of n is equal to 0.54 plus 0.46 cos of 2 pi n divided by capital N minus 1. Once again for the range, minus of n minus 1 by 2 to plus of n minus 1 by 2. Here the value of n is equal to 7, that is capital N is equal to 7. So, the small n ranges from minus 3 to plus 3. Okay. Once again substitute n is equal to minus 3, minus 2, minus 1, 0, 1, 2 and 3. Substitute all the values of n and try to find this W of n sequence. Okay. So, now I got HD of n as well as W of n. Now, third step is we have to find the impulse response of the FIR filter, which is nothing but H of n. H of n will be calculated by multiplying HD of n and W of n. Okay. Once again the ranges are same, the limits are same, that is n is equal to minus 3 to plus 3. Okay. H of minus 3 is nothing but HD of minus 3 into W of minus 3, and H of minus 2 is nothing but HD of minus 2 into W of minus 2, and H of minus 1, H of 0, H of 1, H of 2, H of 3, all the values should be calculated. So, currently we are having all the values. We are in the first step we have calculated HD of n, in the second step we have calculated W of n. Okay. We are having all the values, just do the substitution and get the H of n values. Okay. Here I got H of minus 3 as well as H of 3 is equal to 0.0084, and H of minus 1, H of 2 as a 0, H of minus 1, H of 1 as a 0.0897, and H of 0 as a 0.833. Now, take this H of n values and coming to the transfer function. Okay. So, H of z is equal to H of 0 plus summation n is equal to 1 to n minus 1 by 2 H of n z to the power of minus n plus z to the power of plus n. Okay. Now, the ranges for n is equal to 1 to n minus 1 by 2. So, the value of n is equal to 7, 7 minus 1 by 2 is 3. Okay. So, just expand the summation and substitute the values of H of n, which we found in the previous step. Okay. So, this is a complete H of z. If you look into this H of z, we are having positive value of z also, that is positive power of z also. Okay. Whenever we are getting positive power in the z, which is nothing but non-causal filter. Okay. But FIR filter is always causal. Okay. It is really implementable. Okay. So, we should make that filter as a causal filter. Okay. So, or we should make it as a realizable. Okay. To do that, I am multiplying z to the power of minus n minus 1 by 2 with the entire transfer function to make it as realizable or to make it as causal filter. Okay. Since FIR is always causal. Now, after multiplying z to the power of minus n minus 1 by 2, which is nothing but z to the power of minus 3. Okay. Just multiply z power minus 3 to the entire transfer function, which we done in the previous step. Okay. So, the after multiplication the resultant is this one. Okay. Now, if you see the z power values, z to the power of values, which is always negative. Okay. Which means that which is lying at the right side of your origin. So, I can say it is a causal filter. Okay. Now, the last one, after getting this h dash of z, okay, from this I can able to find the filter coefficients. Okay. From this I can able to find the filter coefficients. The coefficient of z power 0 is h of 0. The coefficient of z power minus 1 is h of 1. The coefficient of z power minus 2 is h of 2. The coefficient of z power minus 3 is h of 3, and so on so. Okay. So, from this transfer function I have written this values. Okay. So, h of 0, h of 1, h of 2 and h of 3, h of 4, h of 5 as well as h of 6. Okay. After writing all this impulse response, I can go for implementation of this. Okay, there are really we will have 3 to 4 different structures. Among that 4 implementations, linear phase is always giving the best output or best way of implementing the FIR filter. So, I have chosen linear phase implementation for this problem. Okay. So, since n is equal to 6, so I can keep 3 delays in the upper portion and 3 delays in the lower portion, that is nothing but this 3 and this 3. Okay. So, now we can implement this is only z power minus 3 x of z. Okay. So, directly I can take here, see this. Okay. And next one is this is z power minus 4 and z power minus 2. So, this value is z power minus 2, this value is z power minus 2, sorry, minus 4, that I have taken here. Okay. Similarly, I can take this also. Finally, I can sum up, this will give y of z. Okay. So, this is the linear phase implementation of the given FIR filter. Okay. Hope you understood. Now, for practicing, you can take these 2 problems. Okay. So, both are design of Bandstop filters. The cutoff frequencies are given. 2 cutoff frequencies are given. One is 1.2 to 1.7. The other one is given in terms of hertz. We should convert in terms of radians per second before proceeding the problem. Okay. So, if you have any queries in this video, you can mail to me at arunkumar@savitara.ac.in. So, I am ready to answer your queries. Thank you.